Function modifiers. Solidity offers a special type of function called a function modifier. You apply modifiers to functions by adding the modifier name in the function declaration. Modifiers are most often used to create conditions that apply to many functions within a contract. We have an access control statement already in our destroy function. Let's create a function modifier that expresses that condition. Modifier only owner, open brace, require message.sender equals owner, underscore, close curly brace. This function modifier, named onlyOwner, sets a condition on any function that it modifies, requiring that the address stored as the owner of the contract is the same as the address of the transaction's message.sender. This is the basic design pattern for access control, allowing only the owner of a contract to execute any function that has the onlyOwner modifier. You may have noticed that our function modifier has a peculiar syntactic placeholder in it, an underscore followed by a semicolon. This placeholder is replaced by the code of the function that is being modified. Essentially, the modifier is wrapped around the modified function, placing its code in the location identified by the underscore character. To apply a modifier, you add its name to the function declaration. More than one modifier can be applied to a function. They are applied in the sequence they are declared, as a comma-separated list. Let's rewrite our destroy function to use the onlyOwner modifier. Function, destroy with no argument. Public, onlyOwner, open brace, self-destruct of owner, close curly brace. The function modifier's name, onlyOwner, is after the keyword public, and tells us that the destroy function is modified by the onlyOwner modifier. Essentially, you can read this as only the owner can destroy this contract. In practice, the resulting code is equivalent to wrapping the code from onlyOwner around destroy. Function modifiers are an extremely useful tool because they allow us to write preconditions for functions and apply them consistently, making the code easier to read, and as a result, easier to audit for security. They are most often used for access control, but they are quite versatile and can be used for a variety of other purposes. Inside a modifier, you can access all the values, variables, and arguments visible to the modified function. In this case, we can access the owner variable, which is declared within the contract. However, the inverse is not true. You cannot access any of the modifier's variable inside the modified function. Contract inheritance. Solidity contract object supports inheritance, which is a mechanism for extending a base contract with additional functionality. To use inheritance, specify a parent contract with the keyword is. Contract child is parent. With this construct, the child contract inherits all the methods, functionalities, and variables of parents. Solidity also supports multiple inheritance, which can be specified by a comma-separated contract names after the keyword is. Contract child is parent 1, parent 2. Contract inheritance allows us to write our contracts in such a way as to achieve modularity, extensibility, and reuse. We start with contracts that are simple and implement the most generic capabilities, then extend them by inheriting those capabilities in more specialized contracts. In our faucet contract, we introduce the constructor and destructor, together with access control for an owner, assigned on construction. Those capabilities are quite generic. Many contracts will have them. We can define them as generic contracts, then use inheritance to extend them to the faucet contract. We start by defining a base contract, own, which has an owner variable, setting it in the contract's constructor. Contract own, address owner, constructor, owner equals message.sender, modifier, only owner, require, message.sender equals owner, underscore. Next, we define a base contract mortal, which inherits own. Contract mortal equals own. Function, destroy with no argument. Public, only owner. Open brace, self-destruct of owner, close brace. As you can see, the mortal contract can use the only owner function modifier defined in own. It indirectly also uses the owner address variable and the constructor defined in own. Inheritance makes each contract simpler and focused on its specific functionality, allowing us to manage the details in a modular way. Now we can further extend the own contract, inheriting its capabilities in faucet. Contract faucet is mortal. Function, withdraw with one argument, uint, withdraw amount. Public, open brace, require of withdrawal amount less than or equal to 0.1 Ether. Message.sender.transfer of withdrawal amounts. Close brace. Function with no arguments, external, payable. By inheriting mortal, which in turn inherits owned. The faucet's contract now has the constructor and destroy functions, and a defined owner. The functionality is the same as when those functions were within faucet, but now we can reuse those functions in other contracts without writing them again. Code reuse and modularity make our code cleaner, easier to read, and easier to audit. Error handling, assert, require, revert. A contract call can terminate and return an error. Error handling in Solidity is handled by 4 functions: assert, require, revert, and throw, which is now deprecated. When a contract terminates with an error, all the state changes are reverted all the way up the chain of contract calls if more than one contract was called. This ensures that transactions are atomic, meaning they either complete successfully or have no effect on state and are reverted entirely. The assert and require functions operate in the same way, evaluating a condition and stopping execution with an error if the condition is false. By convention, assert is used when the outcome is expected to be true, meaning that we use assert to test internal conditions. By comparison, require is used when testing inputs, such as function arguments or transaction fields, setting our expectations for those conditions. We have used require in our function modifier only owner to test that the message sender is the owner of the contract. Require message.sender equals owner. The require function acts as a gate condition, preventing execution of the rest of the function and producing an error if it is not satisfied. As of Solidity version 0.4.22, require can also include a helpful text message that can be used to show the reason for the error. The error message is recorded in the transaction log, so we can improve our code by adding an error message in our require function. Require message.sender equals owner. Only the contract owner can call this function. The revert and throw functions halt the execution of the contract and revert any state changes. The throw function is obsolete and will be removed in future versions of Solidity. You should use revert instead. The revert function can also take an error message as the only argument, which is recorded in the transaction log. Certain conditions in a contract will generate errors regardless of whether we explicitly check for them. For example, in our faucet contract, we don't check whether there is enough Ether to satisfy a withdrawal request. That's because the transfer function will fail with an error and revert the transaction if there is insufficient balance to make the transfer. Message.sender.transfer withdrawal amounts. However, it might be better to check explicitly and provide a clear error message on failure. We can do that by adding a require statement before the transfer. Require with the first argument being this.balance greater than or equal to withdrawal amount. Second argument being insufficient balance in faucet for withdrawal requests. Message.sender.transfer withdrawal amount. Additional error checking code like this will increase gas consumption slightly, but it offers better error reporting than if omitted. You will need to find the right balance between gas consumption and verbose error checking based on the expected use of your contract. In the case of a faucet contract intended for a testnet, we'd probably err on the side of extra reporting even if it costs more gas. Perhaps for a mainnet contract, we choose to be frugal with our gas usage instead. Events. When a transaction completes, successfully or not, it produces a transaction receipt, as we will see in the EVM chapter. The transaction receipt contains log entries that provide information about the actions that occurred during the execution of the transaction. Events are the Solidity high-level objects that are used to construct these logs. Events are especially useful for light clients and DApp services, which can watch for specific events and report them to the user interface, or make a change in the state of the application to reflect an event in an underlying contract. Event objects take arguments that are serialized and recorded in the transaction logs in the blockchain. You can supply the keyword indexed before an argument to make the value part of an indexed table that can be searched or filtered by an application. We have not added any events in our faucets example so far, so let's do that. We will add two events, one to log any withdrawals and one to log any deposits. We will call these events withdrawal and deposit, respectively. First, we define the events in the faucets contract. Contract faucet is mortal, open curly brace. Event withdrawal with two parameters. The first is address indexed to. The second is uint amounts. Events deposit with two parameters. The first is address indexed from. The second is uint amounts. ... Close curly brace. We have chosen to make the addresses indexed to allow searching and filtering in any user interface built to access our faucet. Next, we use the emit keyword to incorporate the events data in the transaction logs. Function withdraw with one parameter, uint withdrawal amount. Public open brace ... message.sender.transfer of withdrawal amounts. Emit withdrawal called with message.sender and withdrawal amounts. Close brace. Function with no arguments, external payable, open brace. Emit deposit called with message.sender and message.value. The resulting faucet.sol contract is in the faucet8.sol file.